Welcome back to part 2 of data structures. In this video we're going to pick up where we left off in the last lecture. So let's get started. When it comes to Java's stack class, Java has a stack class which extends the vector class. The author notes implementation as a subclass of vector and provides inheritance of methods inappropriate for a stack. Let's take a look at an example of building a queue class. In a queue, new values are always added at the front or head of the list. Values are removed from the opposite end of the list, the rear or the tail. Let's take a look at some examples of queues. A checkout at a supermarket, vehicles at a toll booth, or even a ticket line at the movies. When it comes to queues in a computer system, this is when a process or program requires a certain resource. This can consist of a printer, disk access on a network, or characters in a keyboard buffer. We also have queue manipulation operations, such as isEmpty, first, add, and remove. isEmpty returns true or false. First returns a copy of the value at the front. Add, or addB, adds a new value at the rear of the queue, and remove removes and returns the value at the front. When implementing a queue class, we implement as a linked list attribute value. We have insertions and deletions from either end, and this is efficient. This can occur in constant O1 time, and this is a good choice. We can also implement as an array list attribute, but this is a poor choice. We can build a queue from scratch. We can build a linked structure to store the queue elements, and we have attributes which are required, which handle for the head node, handle for the tail node, and an integer to store a number of values in the queue. Here we have a queue structure. We also have the my head, my size, and my tail, which all branch off to other sections of the code, as you can see here, or in this example, the diagram. We have queue class methods, which consist of the constructor, isEmpty, and front. Each do different things. The constructor sets my head and my tail to null, or sets my size to 0. isEmpty returns results of comparison, and the front returns my head.getValue, unless it is empty. We have add and remove. Add creates a new node and updates the attribute variables. If the queue is empty, it must also update my head. Remove must check if the class is not empty. Otherwise, it saves the handle to the first object, adjusts the head to refer to node, and updates my size. So now let's move on to an introduction to trees. We seek a way to organize a link structure so that elements can be searched more quickly than in a linearly linked structure. This also provides for easy insertion/deletion. It also permits access in less than ON time. It can recall binary search strategies and look in the middle of a list. Let's visualize a binary search. Here is this drawn as a binary tree. When looking at tree terminology, a tree consists of finite collections of nodes. Non-empty tree has a root node, and a root node has no incoming links. Here we have our leaf nodes. our sibling nodes, our parent and child nodes. When it comes to applications of trees, we have a genealogical tree, which pictures a person's descendants and ancestors, and game trees, which shows configurations possible in a game such as the Towers of Hanoi problem, or parse trees, which is used by the compiler to check syntax and meaning of expressions, such as 2 times 3 plus 4. We have binary trees. An example of a binary tree consists of each node has at most 2 children. Useful in modeling processes where a test has only 2 possible outcomes. These consist of true or false, and a coin toss such as head or tails. And a binary tree can be applied to decision trees in expert systems of artificial intelligence. When it comes to implementing binary trees, each node has 2 links and a handle to the data. One link to the left child, and the other links to the right, as you can see in this example right here. We have the declaration of binary tree node in class right here. As you can see, the public class is binary tree node. Binary tree node is only one of the attributes of a binary tree class. Again, here's another example. Feel free to test these, play around with them, or just simply try them out for yourselves also. When we visualize a binary tree, this is what it looks like. Again, it is kind of like a tree with branches branching off of the main code. There are binary search trees. We can have a search algorithm which initializes a handle such as current node to the node containing the root. It will repeatedly do the following. When constructing binary search trees, the descend tree should be looking for a place to insert the item. We set the parent node to the current node. We change the current node to its left or right child. If the value being inserted is not in the tree, current node will eventually become null. The parent node will indicate the parent of a new node to contain the value. There is also tree traversals. A traversal is moving through the binary tree, visiting each node exactly once. With a traverse algorithm, we have 1. Visit the root and process its contents. 2. Traverse the left subtree. When it gets into the subtree, it visits its root and processes, traverses to the left sub-subtree, and then traverses to the right sub-subtree. And 3, we have traverse to the right subtree. Again, it is as if it is moving through different branches. The tree traversal is recursive. If the binary tree is empty, then do nothing. So else, L, traverse the left subtree, N, visit the root, or R, traverse to the right subtree. This is the anchor. This is the inductive step. Let's move to the traversal order. There are 3 possibilities for the inductive step: left subtree, node, right subtree, and the in-order traversal. Node, left subtree, right subtree, the pre-order traversal, and left subtree, right subtree, node, the post-order traversal. With other data structures, the set interface is implemented by the hash set and the tree set classes. We've looked at all of these in previous lectures. The map interface is implemented by tree map and the hash table classes. And collections class is a variety of utility methods for manipulating collections. That's the end of this lecture. I'll see you in the next one. Be sure to keep practicing, and if you have any questions, feel free to ask us in the discussions. I'll see you guys in the next lecture.